In this exercise, we're going to build a blackjack game. So if you've never played blackjack, the first thing I'm going to say is go get a rough overview of what the rules of blackjack are. We're not going to use all of them. We're basically just going to use a very small subset of what you traditionally see at a blackjack table in a casino or something like that. But blackjack is a fairly simple game. So even if you wanted to implement all the rules, which are some of the bonus exercises here, it's nothing that's so crazy that it'll take you days to learn the game or anything like that. It's a relatively simple game with a small set of possibilities you can take, or a small set of possible actions you can take. So it shouldn't be too rough there. The other thing to mention is that this is going to be using the package that we created in the last exercise. So in the deck of cards exercise, which is linked here, you'll need to either write that, go through the exercise, perform it yourself, or the other thing you might want to do is go check out the code, clone the Git repo. If you do that, make sure you set it into your Go path, so you can actually use it, but also make sure you check out the P8 branch that I have linked here. As of right now, that's the most recent branch. I don't have all that code checked into master because I don't want people doing this exercise to accidentally just see all the source code and the solution to the problem. So I try to keep things out of master, but as a result, it's easy to check it out, not actually have the package available, and then wonder what's going on. So just keep that in mind. If it does end up causing issues, let me know. I'll try to come up with a better solution, but I don't know one off the top of my head right now. Okay, so now that we have that deck of cards to work with, you've gotten it in your code. The basic rules for the game we're going to have. First is every player gets dealt 2 cards. So typically in a blackjack game, you'll have a set number of decks. Whether that's 1 deck of cards, 2, 3, that's kind of up to you. I'll probably use like 3 in our game just because 1 is small enough that if you get more than 2 players, it goes very quickly. But 3 decks is enough that you could have 3 or 4 people playing against a dealer. And long term, we're going to want to probably try to code that up. So 3 decks should be enough that that's possible. Counting cards is a little bit trickier for a human player at least, and it'll be interesting to work with. So when cards are dealt, you start with the players. The dealer's the one dealing the cards, in a casino. So he'd start with the first player to his left, and then he'd go clockwise. So in your case, just assume you start with the first player, go through all the players, and then the dealer gets dealt a card. And then you repeat till every player has 2 cards. Whenever the game starts, every player can see each other's hands. That's just kind of how the game works, at least in a casino. And the dealer, you can only see one of their 2 cards. So just keep that in mind that when you're writing the player's AI or just playing yourself, you shouldn't see both the dealer's cards. You should have to sort of make decisions based on the one card you see while not seeing another. In a player's turn, the first version of this game, I'm going to suggest just keeping it really simple. Allow a player to hit, which means they're going to draw another card, or stand, which means their turn's over, they're okay with the cards they have. So the dealer's turn, in the first iteration, I would probably just not even have the dealer do anything, because in order to have a dealer do something, you need to have some code that allows you to score. So you have to be able to score a hand. First version of this game, I would really suggest just not even bothering. I would let the player play, and at the end, just show all the cards and let the player decide if they won or lost. Second version of the code, I would come back and I would add in some scoring, and then I would add the dealer's turn. So the AI there is basically going to be if the dealer has a 16, they hit, or if the dealer has a 17, but it's a 17 with an ace that counts as 11 points. So in blackjack, an ace can be 1 or 11 points. It's the player's choice. Technically, it's whichever one's better without going over 21. So in that case, if the dealer had a 17 where one of those was coming from an ace that's 11 points, they would still hit on that case too. And, just so you know, that's pretty traditional, the way a dealer would operate in any casino. That's why I sort of stuck with that. You could change it if you want to tweak it and sort of try things. There are some slight variations you'll see in casinos, so it really depends. All right, then determining the winner. I mentioned this earlier. First version, I would not actually have your code calculating a winner. Second version, you want to calculate the winner. Whenever you're looking at the cards, it's whoever has 21 without going over 21. The player will have, if they bust, if they go over 21, it doesn't matter what the dealer does at that point. The player's already lost. So cards 2 through 10 are worth their face value. Jack, Queen, King are worth just 10 points each. And the ace is 1 or 11 points. So the ace is the trickiest one to sort of code up because it's variable. And you'll see when we code this, it's actually not that hard to code the ace because, the highest score you can have is 21. So if you have two aces, you know that one of them has to be 1 point. The other one can be 11 or 1, but two 11s is 22, so clearly that'll never happen. So it actually ends up being pretty simple. There's a little bit more here that talks about some of it, and you should definitely look up blackjack rules if you're not familiar with them. So bonus exercises. This is the stuff that really expands upon this, in my opinion. So there's a lot of things you can do here. You can add in the new rules, like allowing the players and dealers to win immediately with blackjack. So whenever a player gets dealt a blackjack, an ace and a 10, or an ace and a face card, usually they have blackjack right away. And they just win. They get paid out some different amount. I forget exactly what it is. Maybe it's 1.5 or 2 to 1. It's usually a little bit extra you win for getting blackjack. The other thing is if the dealer gets blackjack. So if a player is playing a casino, the dealer has blackjack, and before they even get to play, usually the dealer would check to see if they have blackjack, and if they do, everybody on the table just loses. There's other things like insurance that you could look into for gambling and that sort of aspect of it. But it's kind of up to you there. The second thing that you might want to implement here for the bonus stuff, which is related to all that, is the betting aspect. So you might want to add a way to keep track of a player's score, allow them to play multiple hands. And by score, I mean like their total pot. Let's say they start with 100 coins. Let them bet different amounts of coins and win earnings based on how much they bet. And then you can sort of keep track of what a player's total net winnings or net losings are, or whatever, based off of that. So there's other rules in the game too that I didn't mention here. If you've ever played blackjack, especially at a casino, you'll probably know about splitting and doubling down. You could add those in your game if you want. You could also add additional human players, or just have human players replace yourself entirely and turn this into a simulation. So the way we're going to code it, the first versions probably will be pretty hard coded into having a real player there. But I'm going to try to code mine so that we can substitute a real player with an AI of some sort, and then we can start doing things like counting cards, looking up strategies online so that we can actually figure out what's the optimal strategy based on what we've seen. And you can basically start adding that sort of thing, and then you can run the simulation thousands of times and actually see if your AI is ending up coming net ahead or net behind, and what the AI is like. Now, this isn't quite exactly the same as actual statistics to figure out this is the best strategy. But if you run it enough times, you should actually start to converge on things that are similar to what you'd expect. So, for example, if the house has a 1% edge, you would traditionally expect to see the player gradually losing a certain amount of games. And then if you take in things like counting cards and increasing or decreasing your bet based on what odds you think you have, then you should start to see your players start to win more often. And that's why casinos will typically kick somebody out who's counting cards and stuff like that, is because you can actually take the edge away from the dealer or the casino if there's a limited number of decks and a player knows what they're doing with counting. So I think that's everything for this. Go ahead and jump into it. I don't know how much of this I'm going to do in the videos. I don't know what other stuff I'm going to add. I have a rough idea that I want to just make this blackjack game because I just think it's a fun little thing we can do, especially the simulation side. Once you get the game working, it's cool to see how you can just take a game you wrote and plug in an AI and get it to start playing the game and doing stuff. To start the exercise, I think the best way to start is just to go ahead and create a main file. And then inside of that, we just want to make sure we can get a deck of cards that's, maybe let's say we want to do 3 decks of cards all in our deck and we want to shuffle them. And then we want to be able to draw cards from that deck. So I think just starting there is a good spot to start. And then from there, we'll move forward into, actually creating a player and a dealer, setting up their hands and just getting the basic functionality of the game working. So we're going to start with code main.go. So I'm using VS Code now. I was using Atom in a lot of the past videos, but it's the same thing. I'm just opening up main.go in my editor. And I'm just going to close that. So we're going to go ahead and just create the package main stuff. And then inside of here, I'm going to say cards is going to be deck.new. So deck is the package that we have. So if I come up here and import github.com/Gophercises/deck, that should give me most of this. And then inside of here, I want deck.deck. So this is the functional option we had before that allows us to say how many decks of cards we want in this. Looking at it now, it might not be the clearest name, but I think that's fine. So deck.deck3, and then we want to do deck.shuffle, so it shuffles all of those. So from there, I think the next thing we're going to do is just iterate over, let's just say 10 cards. And we want to go ahead and draw cards from the pile. So drawing is, there's different ways to do it. I think what we're going to do is we're going to take from index 0, and then we're going to update the card slice so that it no longer has that card. So we're going to say card, cards. Actually, we're going to go ahead here, and we're going to say var card deck.card. And then here we're going to do card, comma cards equals, we'll do cards 0 for the card, and cards 1 colon is the rest of the cards. So we're basically saying that we're going to set the card slice to just be all the cards except for the very first one. And then we're going to say the card we're drawing is that very first one. So this is just a nice, easy way to sort of pull those out. And then let's go ahead and print line that card. All right, so that should be everything we need for that. So let's just go ahead and run it and see how it goes. So it looks like we're doing 2 of clubs, 5 of hearts. These all appear to be pretty shuffled. You will see there are some duplicates. That's expected because we have 3 decks right now. And if we run it a couple times, we seem to be getting different results every time. So, the shuffling appears to be working roughly as we expected. Okay, so from there, we're going to need some hands. And a hand is basically just a slice of cards. So we could go ahead and just use that type for our hand. There are a couple reasons why we might want to create our own type, though. For starters, it might just be easier to print these out. So I'm actually going to go ahead and just create that now. Type hand is going to be a slice of deck card. And then I want to add a way to print this out. So I'm going to say func h hand, and we're going to do string. So string is the function that gets used most of the time, or should get used whenever we're printing things out with print lines, stuff like that. And what we're going to do here is I just want to take all the cards in the hand and I just want to make them a comma separated string. So if you print out a regular slice, let me go ahead and just show you this. If we were to print out cards 0 to 3, and I'm just going to return an empty string up here so this compiles. Now if we were to run this, you'll see at the very end that we get this. Now that's clearly, it's not super clear as to what's the separation. There's no commas in between them. So it's just not quite as clear as I'd prefer it to be. So what we're going to go ahead and do is we're going to go ahead and try to make something a little bit clearer. So I'm going to say the strings are going to be a slice of strings that have a length of whatever the length of h is. And then we're going to iterate over h. So for each index in h, and it's very important you realize that this right here is an index still. If you put a comma and then another variable, that one will actually be the values inside of the hand. But the first one is always the index. So with this, we can actually say the string at index I is going to become whatever card is in the hand at index I, and we're going to use its string function. So that's what's getting us like the ace of spades, things like that. So finally, we're going to return strings.join, and we're going to join them with a comma like this. And I'm going to put a space afterwards. And this will go ahead and insert that comma in between all of them except for the very last one. So now, if we were to go run, this is still the same because this isn't a hand. But if we were to go ahead and say var h hand equals cards 0 to 3, and you'll see here this is probably going to complain. So if we do this, this should work. I actually don't know if we need to do this part. Nope, appears to be fine. Okay, that was, I guess, just inferred. So now if we run this, you'll see that when we print out the hand, we get King of Diamonds, 5 of Hearts, Queen of Hearts. So all of that is there. It's all what we expected it to be. It's just a nice, easy way to print out these cards. So now that we have a way to represent a hand, I think the next step is to create a player hand and a dealer hand. So let's go ahead up here. We want to keep the deck, but really the rest of this probably doesn't need to stay. I'll keep the card because we're probably going to be drawing with it. So from there, what we're going to do is say var player, dealer, and these are both hands. And then we're going to go ahead and iterate over each hand. So for each hand in the range of, well, we'd like to sort of just make this easy. We want to iterate over both of these as we're dealing to the players. So I think what I'm going to go ahead and do is just say that I'm going to use a slice of pointers to hands, and then do and player and dealer. And that'll give me, a way to access each of these in a simple for loop without having to, redo that code. There are other ways to do this. This is just sort of a quick shorthand way that I think works pretty well for what we're doing here. So then in here, we're going to say card, draw pile. So our draw pile is cards here. And then we're going to say it's equal to cards 0, cards 1 onwards. And then we want to go ahead and say that the hand is going to be append whatever's in the hand with the card. And you'll see here that I'm using these asterisks. That's because this hand here is a pointer to a slice. It's not actually a slice. Well, technically it's a pointer to a hand, which is a slice of cards. So it's a pointer to a slice, essentially. So if we want to do this append, the easiest way is to go ahead and put the star or the asterisk in front of both of these, which says that I don't want to deal with the actual pointer. What I want to deal with is the value that it points to. I want to go ahead and update that. So I'm saying whatever value this hand variable points to, I want it to now become the slice that comes out of appending whatever value is there with a new card. And this pointer stuff is something that can be a little bit confusing, especially when you're first getting into Go. I know that when people learn C and some other languages like that, the pointers can be pretty confusing. So the best I can say is experiment with it, mess around with it. It does start to make more sense after a while, but it can be a little bit weird at first when you're just not used to it. Okay, so after that, let's go ahead and print these out. And we'll do dealer. And each player and dealer are both just going to have one card right now. We'll add a second one. We want it to be 2 cards per person. So we're going to go ahead and just add an extra loop here. I is 0, I is less than 2, I plus plus. So we're saying each player gets 2 cards. And you'll see here that by writing our for loop this way, we made sure that we give the player a card, then we give the dealer a card. And then we go ahead through this loop again and we do the same thing. So we're dealing exactly like we would in a regular casino. All right, so let's go run main.go. And we'll see the player has 7 of spades, ace of hearts. The dealer has 3 of diamonds, queen of diamonds. Okay, so we've got these hands drawn. One of the things that might make sense at this point is to add a draw function. I think this logic is simple enough, but it's not necessarily clear what it's doing. So if you really wanted, you could pull that out into a func draw, which takes in a slice of cards. And we'll say maybe it returns a deck.card and a new slice of deck.cards. So this is just going to be this part here. We would just return that. It's really simple. The only real reason for this is that whenever you draw, you do this. And just maybe it just becomes a little bit clear as to what this line is actually supposed to be doing. You see this draw function, you're like, oh, they're drawing cards. Now, there are downsides to that. Now, if somebody wants to see how draw works, they have to go find that function and look at how it works. So there's a little bit of indirection there. So it's kind of up to you as to whether or not you think it's worth splitting into a function. I'm going to leave it just because I wrote it that way for now, because I've already written it. But yeah, you don't have to do that, obviously. Okay, so there's a couple things that we have missing here. One, we don't have any way for the player to play yet. And 2, the dealer hand is clearly very visible here, and we don't want it to be visible. So I think it's easiest to tackle the dealer hand part. So we're going to go ahead up here. And rather than creating a separate type for the dealer, which we could do, I think for now I'm just going to go ahead and just start with a single function, or just a method on top of this hand class, or not class, wow, struct type. So I'm going to call it dealer string, and it's going to return a string. And basically this is just going to be the version that we call for a dealer. So I'm going to return h0 not string. So this would be the first card in their hand. And then after that, I'm going to return just a hard-coded string that's a comma and then hidden for the second card. So knowing that, we can come down here and we can do dealer string. And that should All right, that updates this for us. And you'll see here that, oddly enough, they both got a 5 of clubs, and then one has an ace of hearts and the dealer has something else. So if we keep running this, you'll see that every time the dealer has a hidden card. Okay, so the last bit, at least in this video, is I want us to have some very basic game logic. Specifically, I want to deal the cards, I want to show the cards, and then I want to let the player decide if they want to hit or stand. And if they decide to hit, we're going to draw another card for them. And then once the player does decide to stand, we're just going to show them the final hands. So instead of doing dealer string, we'll actually show them the true dealer's hand. And then they can decide from there whether or not they won or lost. We don't actually have to be involved in that this first version. So to do this, I'm actually going to keep this stuff here, but I'm going to go ahead and just put some code above it. So I want to get some user input, so I'm going to go ahead and just make a variable for that. And then I'm going to say while the input is not equal to S, which is going to stand for standing. So as long as the user hasn't decided to stand, we're going to keep on running this loop. And inside of this loop, we're going to print out the player's hand, print out the dealer's hand, with a card hidden. And then we're going to print out a message that says, what will you do? Hit. And then we'll put stand. And I'm just going to separate these with a comma because later we might add some extra options. So just keeping them comma separated will be easy. And then we need to read in the user's input. So I'm just going to use scanf for now. And we'll do and input is where we want that variable, the input to be stored. And then we're going to switch on that input. And we're going to say that if it's an H for hit, then we need to draw. So we're going to say cards equals draw cards. And then we're going to say player is equal to append player card. And I do want to mention here that I'm not using the asterisk that you're seeing up here. There's nothing like that going on. So the reason that happens up here is because I've got, this is a slice of pointers to hands. And each of these, you can see I put the and in front of it, which means I want a pointer to the player hand and a pointer to the dealer hand. So whenever I actually want to reference the value that's stored by that pointer and not just the pointer itself, I'm putting these asterisks here. But down here, when we declared player up here and dealer, you'll see that neither one of those are actually pointers. So when I'm doing this down here, I don't actually have to do that. And you're probably a little bit confused as to why I'm doing that. A big part of it is because when you're running for loops like this, especially when you're using the shorthand where you've got this second variable here, it's very easy for that to end up being a copy of the data you're working with and not realize that it's a copy. So, another way to get around that is you could say J here, and then if you actually had this slice stored somewhere that you could actually access the individual pieces of it, that would work. But since we don't have that, we're going to use a little bit of pointers here to make sure that we can actually edit the actual player and dealer variables, and not a copy of them, because that's what this could have been. Okay, so I think down here in this switch, we say if it's a hit, we're going to go ahead and give another card. If it's a stand, we don't actually do anything in this switch. So the switch is going to look really weird just with one option, but I think it makes sense because it kind of infers that in the future we might have more options. We know that. So, we're just going to go ahead and start with that. And you could also add something like case S, print nothing, and you could add a default case. That is, if they didn't print out an S, then we want to tell them, hey, that's not a valid option. Okay, so after we've done all of this, the last thing is just printing out the final scores. So let's do final hands. And I'm just putting some equal signs in there just to sort of keep a separator or something like that that'll make it obvious that it's the end of the game. And we'll say player. And I'm going to go ahead and copy this and do dealer. And then we don't really need to print anything. The player can decide if they won or lost, but we don't really have to keep track of that right now. Long term, we might want to just say, did you win or lose? But we also know that what we're probably going to end up doing is just actually calculating scores of knowing who won or lost. So, there's no real point in spending a lot of time doing that. So let's go ahead and run this. I want main.go, not main. All right, we have a jack of hearts and a king of clubs. Well, if we hit on this, we're going to bust almost guaranteed. So we'd probably want to stand here. And then we would find out that the player has a jack of hearts, king of clubs, and the dealer has a 9 of diamonds, 7 of diamonds. So if we had an AI, the dealer at this point would probably have hit. But since we don't, we're going to go ahead and just keep our game pretty simple as it is. So this isn't a perfect version, but I do think it's a decent one. Again, I'm going to go ahead and try to do this until, all right, we would want to hit here more than likely. So we've got a 3 of spades, 9 of spades, we hit, we got an ace of hearts. I'm just going to keep hitting just to sort of show you that it works. So now, we've got 4 cards, and if we keep hitting, we'll keep getting new cards over and over again until we finally stand. And then if we were to type some gibberish, you'll see here that it just repeats the same thing over and over again. It doesn't actually say this is an invalid input, but I think it's pretty clear by nothing happening that you need to choose one of these options. Okay, so that's it for the first video. In the next video, I think what we're going to do is add a way to score hands and add a player or a computer AI so that we can actually, do something with this. Start building out the other parts of this. But for now, I think this is a really good starting point. The goal in this video is going to be to write a method on this hand type that allows us to calculate a user's score. So we're going to start off with just doing the minimum score. So we're going to assume that all aces are 1 point. And as we write this, you'll see why that is helpful. Most notably, if we know what the minimum score is, we can go through and figure out, can we turn any of these aces into 11 points instead of 1? So the minimum score allows us to, quickly determine that without worrying about busting it, or while considering things like busting, not necessarily not worrying about them. And we're going to need to do this first because we want to add some sort of AI for our dealer. So right now, our game, when we play it, and at the end it shows us all the hands in our card, but the dealer doesn't do anything. They don't really have any sort of strategy. They just take whatever 2 cards they have, and that's the end of it. And we also don't show in our game, did you win, did you lose, nothing like that. So we want to get the notion of scoring so that we can add all that sort of functionality. And it's especially necessary for the dealer because the dealer can't decide whether to hit, stand, or anything like that without actually knowing what their score is. So it's important to have some way of getting that score first. So we're going to be adding this on the hand type. So I'm just going to start up here. It's going to be func. I've got to get my hands on the keyboard correctly. And as I said, we're going to start with a minimum score, and it's just going to be an integer. So this is going to be, some integer value, typically between 0 and 21. I guess technically it's got to be at least 2. But, it's going to go ahead and take a hand and calculate the score. It's not going to worry about busting or anything like that. It's just going to return whatever the score happens to be, so we can work with that. So we're going to start with the score is going to be 0, and then we're going to return that score once we've calculated it. So in order to calculate it, we're going to look through every single card in a player's hand in range H. And we're going to go ahead and add the, whatever value that card should be. So the easiest way to do this is to say score plus equals c.rank. But there's a problem here. Some of our cards are going to have a higher rank than 10. So our jack, queen, king, and ace, actually the ace has a rank of 1, so that would be fine actually. But the jack, queen, king all have ranks of 11, 12, 13. And realistically, they're worth 10 points in blackjack. So the easiest way to fix this is probably just to create a minimum function that takes in 2 integers and returns the minimum of the 2. And I will say that it is a little weird using a writing a minimum function like this, because a lot of languages will provide something for you. And if I recall correctly, Go has one for floats, but I think it's like math.min. Yeah, so it's going to return some floats. The problem is I find converting numbers into the float type and then coming back to the integer type and doing all that work, it's just as easy just to write a real quick minimum function, and then it's much easier to use inside of your code because it's type safe. You don't have to worry about any of that other stuff. So we're going to go ahead and use that, and we're going to say we want the minimum of the rank, and the other option that we have is 10. So basically what we're saying is if we pass in a rank of 11, 12, or 13, we want to just count it as 10 points. So I think that's all of this, although we're probably going to have to do something about this rank. So this rank, if you look at the error, it's going to say that it's a type rank, and it's not an integer. But we know that this type, if we were to go to the definition, that's not what I wanted. Let's go to the definition. You'll see here that up here, it ends up being a type of uint8. So, it is an integer value of some sort that we can use. So knowing that, we can just, convert this into an integer here, save it, and our code starts working again. Okay, so now that we have all this, we're going to go ahead down here, and we're going to go ahead and add a score. So I'll do a new line, I'll say score, and then we'll add player.score. We want min score here, actually. And we're going to do the same thing down here, and this is going to be dealer.minscore. Okay, so now if we run this, let me clear all that up. And actually, let me make this a little bit smaller. It's taking up a lot of my screen. All right, so go run main.go. So we've got a 7 of diamonds, queen of diamonds. If we stand here, you'll see that it's giving us a score of 17. It's giving the dealer the score of 14. So that seems to be working. I'm going to go ahead and just do this a couple of times until we get an ace, although we did have that there. So 7 of clubs, ace of clubs, you can see that that's working correctly. We can do this a couple more times and see if we get a face card. So there's a jack of spades. It should be counted as 10 points plus the 9 is 19, and that's what we're getting. So it looks like all of these are working. You could write a test for that if you wanted, but for now I'm just going to let it be. So what we want to do now is we want to go ahead and write a real score function. So we want something like score that just returns their maximum possible score. We're going to keep min score as an exported type. Technically, we're not really exporting any of this because it's all in a main package, and that's how we're using it. But I'm going to keep both of these this way because realistically, sometimes knowing if the min score is different than your max score is useful, especially when you're trying to figure out your AI. Are we using an ace for 11 points? Well, if you are, your min score and your score will be different. So inside of this, we're going to say min score is colon equals h.min score. So now we have a minimum score to work with, and we're going to say if our min score is greater than 11, we're just going to return the minimum score. And we're doing this because if we have a minimum score of, say, 12, well, we can't take a card that's worth 1 point and make it worth 11 points because that would add 10 points to our total score. So a 12 plus 10 is going to be 22, which is a bust in blackjack. So anytime we have a minimum score greater than 11, we no longer can count aces as a 10, as an 11. So the next thing we want to do is go through our cards and see if we have any aces. So you can tell that if we don't have a single ace in our hand, obviously our score is just what our score is. Ace is the only card that has 2 possible options. So we're going to say if c.rank is equal to deck.ace. And if it is, now we have this option of returning a different value. Specifically, we can return min score plus 10. And I'm doing plus 10 here because ace is currently worth 1. And we are changing it to be worth 11. So 11 minus 1 equals 10. So that's the delta that we need to increase the score to make that happen. And we only need to do this once because if we had, let's say we had 2 aces in our deck, and that's the only cards we have a score of 2. If we were to change one of those aces into an 11, we would now have a score of 12, which, as we saw earlier, means that we cannot increase, we can't use aces as an 11 any other times because it would make us bust. So we can only actually use one ace as 11 points, so that makes the logic here pretty simple. Otherwise, if we get through this whole for loop and we haven't found an ace we can use, we return min score. All right, so that should give us our real score. So we're going to come down here, and we're going to print out score and score. And now we're just going to go ahead and go run. I don't know why this keeps getting bigger, but whatever. So we have, all right, the dealer has an ace, so we can see. All right, it looks like the dealer's getting a score of 12, which is correct with 2 aces. All right, so that's all that we need for the scoring part. Now let's go ahead and look at how do we go about adding, something for the player. How do we add something that says, you busted, you won, you lost, something along those lines. So we're going to do this before we add the dealer AI, so that when we add the dealer AI, or 1, just because we have all the pieces necessary, and 2, just so when we add the dealer AI, it's there. So we're going to say player score, the dealer score is equal to player.score and dealer.score. And I'm doing these right now. I'm actually move these up. I'm storing these in variables because every time we call player.score and dealer.score, we have to calculate it. So I'm just doing this so that once we've calculated it, we don't try to calculate it multiple times. So over here, I'm going to replace this first one with P score. And then I'm going to replace this with D score. And then we want to see who won, who lost, what was going on. So I'm going to switch. And then inside of this, I'm going to put the cases that I think are worth looking at. So the first is if the player score is greater than 21, then we're going to just print out you busted. So this is the case where the player lost. The other case is if the dealer score is greater than 21, then the dealer busted. And we're adding this afterwards because I think I mentioned this before. If a player busts, it doesn't matter what the dealer does, the player's already lost. So, we only get to this case if the first one didn't fall through or didn't, if the first one was, what was caught, the second one here shouldn't be, even tested. So third, we have case, if the player's score is greater than the dealer's score, then we're going to print out something like you win. We'll put an exclamation mark here, that's fine. Otherwise, if the dealer's score is greater than the player's score, and you'll notice that both of these come after we check to see if anybody has a score greater than 21. So we're trying to make sure that anybody who has a score greater than 21, they get that situation is handled first. So in this case, we're going to print out you lose, and then finally, if the scores are equal, we'll print out draw. And there's other things you could handle here. For instance, if you wanted to look for blackjacks, that sort of stuff, you could add that. But blackjack, I will mention, is going to be a little bit trickier. You'll probably need to add a method to your hand type that tells you if it's actually a blackjack, because you'll need to look at the cards and see, is there an ace and a 10 value card to get blackjack. All right, so let's go ahead and run this. All right, king of spades, 3 of diamonds, we'd probably want to hit here, and then we'll stand when we get 19. So you'll see that it says we win because we have 19, the dealer has 17. And if you run it a few times, this should, continue to work correctly for us. If we lost, and you'll see that it's saying you lose. So it looks like it's working. Let's just go ahead and try the bust. Even though we don't have any logic that prevents me from continuing to draw, it'll still give us a right score. All right, so it says we busted. Okay, so we've got all of that working. That's it for this video. In the next one, what we're going to look at is adding some logic for the computer AI, which is actually pretty short, so I take that back. Let's just do that now so it can just all be one video because it's relatively short. So the way the AI for the dealer is going to work is once the player's done, so once we're done with this for loop here, we're going to go ahead and figure out what the dealer wants to do. So the basic strategy for a dealer is if dealer score is less than or equal to 16, we hit. And the other option is if the dealer has a soft 17, then we hit. So a soft 17 happens when you're counting an ace is 11 points and your score is 17. So what this really means is if the dealer has a score of 17 and they have a minimum score that's less than 17. Specifically, it's going to be something like, well, there's only the one situation that'll get caught by that, but I'll show you here in a second. So we've got dealer.score is less than equal to 16. So that's the first option. Or if the dealer.score is equal to 17 and the dealer.min score is not equal to 17. Now you'll see here with all of this, it's going to be a little slow because we're calculating all these things many, many times. I'm going to let it be for now. It's not super slow to calculate scores because a person's not going to have more than maybe 5 cards in their hand, so it's really not a big deal. But if you're really trying to optimize things, you might want to look at this and figure out, can I store these in variables, and then can I use those and re-update them every time this happens? The other thing I'm going to do is I'm actually going to change this to be a for loop, not an if, because I want this to run every single time until the dealer stops matching these criteria. So inside of here, we're going to say cards is equal to draw from the cards. And then we're going to say the dealer is equal to append dealer card. So just like before, we're hitting at this situation. We're adding a card for the dealer. All right, now let's go ahead and test this. And we have 20, so we'll stand. You'll see here that they had a hard 17, so the dealer didn't do anything. But I want to see what happens when the dealer does have something. So you'll see here they had a 2 of diamonds, queen of diamonds, that's a 12. So the dealer has a 12 score, so they hit. Then they have a 14 score with the extra 2, so they hit again. And then finally it goes up to 18, and the dealer quits hitting. So it looks like that's working for us. The only thing that we're not seeing right now is a soft 17, which is a little bit trickier to just randomly run into. So one of the things you might want to do is just sort of intentionally write a test to verify that use case works. That's the type of thing where you can't just run it manually in your terminal and really get a good idea of whether or not your code's working, because it's a kind of rare situation. So that's definitely a place where either writing a test, or maybe it makes sense to just update your main to sort of hard code the cards and just make sure that works to keep yourself happy. But I think a test would probably be easier here. All right, so that's it for this video. In the next video, I think what I'm going to try to cover are game states. So I'm going to sort of show you how you can take this design that we have with our code, where pretty much all the logic is just jammed into this main function. We're going to look at how we can break things up into functions that modify a game state object. So we'll be able to use that to expand on our game, and it will make it, when you add new rules like splitting and all that other stuff, easier to add to your game, because it's not just piling onto this massive main function. It ends up being smaller functions that are much easier to write, that have separate responsibilities for what they're supposed to do. In this video, what we're going to do is refactor the code we have, and we're going to introduce something called a game state. Now, I'm not a game developer. There are probably some ways that this could be optimized. There's a lot of different things you could be doing, but basically what I want to show you here is that we can take everything that we have, everything in this main function, and we can sort of represent the state of a game at any given time as an object. And then once we have that object, a lot of our game can turn into a series of functions that essentially take the object, perform some manipulation or transformation on them, and output a new function. A new game state. And the reason that this is useful is that at any point in time, if we wanted to save the game, or if we wanted to replay the series of steps that were taken, all we'd essentially need is a game state. So if we wanted to replay, we'd need the original game state and a series of the functions that were called to cause those transformations. Or similarly, if we wanted to save a game to then resume it, we would only have to take the current game state, save it somewhere, and then when the user came back and said, hey, I want to resume my game, all we do is load that up. Now, there's a bunch of other benefits too. It makes a lot of this code, in my opinion, easier to expand upon later. It's going to make it easier as we start to add other things like gambling and that sort, betting and that sort of thing to the game. Not true gambling, because obviously we're not dealing with real money. But as we add those aspects, you'll see how they're easier to do with this game state, because there's a lot less you have to think about. It also makes it easier to do things like verify that we're in a correct state, that we can actually do what we expected to do. For instance, once you introduce betting, you don't want somebody to bet after a hand has been dealt, so you might have some checks like that in place. Now, we're not going to do this exhaustively. This isn't going to be a fully featured legit blackjack game. The idea is to get most of the functionality there so that we can write a quick simulation, test it out, see how it goes, and just do something a little bit fun with it. So before we do that, I want to talk about game state. So looking here, the top has what I would consider a potential for a game state. So the first thing here, all of this section here. So the first thing here is a deck. If you look at our main.go, you'll see that we create a deck of cards, and then the rest of our game involves drawing cards from that deck, dealing cards from that deck. So at any given time, in order to actually play our game, to represent the game state, we need to know the deck of cards that we have. In our case, it ends up being a deck that actually has 3 decks of cards in it, and they're all shuffled, but that's what I'm trying to represent here with this first line. The second line, let's skip that for now. The third line is going to be the current player's hand, and the fourth line is the dealer's hand. So these are pretty obvious. It's which cards are in their hands that they're playing with. As we start to introduce new things, the way we represent this in memory might need to change, but the basic idea is the same. So for instance, whenever I say we might need to change it, what I mean is, let's say the player had a 10 and a 10, and we introduce the ability to split. Well, obviously the player's then going to have two hands. So if you're familiar with blackjack, you know splitting means to split your hand into two hands. In order for that to be the case, we would probably have to change this data structure so that, you know, it's not just a hand. Maybe it's a slice of hands for the player. You know, it's kind of up to you. And then we're also going to have things like betting, you know, all sorts of stuff like that. So again, the data structure might change over time, but the idea here of we need one thing that represents the entire game at any given time is staying the same. So the turn up here, this is something, there's basically going to be two elements to this in my opinion. The first is what sort of stage in the game we're at. So, you know, maybe it makes more sense to call this a stage or something like that. But the idea here is that in any given time in a game, there are different sort of you know, spots we can be in the game progress. So let's say we added in you know, betting. We might first say before the game even starts, we need to create, you know, shuffle the deck. We don't have a deck, so we need to shuffle or create a new deck and shuffle it. All right, so then once we've done that, the next step might be, you know, we have a proper deck, so we want players to bet. So now they're in the betting stage. After players bet, maybe we deal hands. So we're in the dealing hand stage or something like that. And then after that, we go to the first player's stage. You know, so it would be player's turn or something. So there's all these different states that we might have that sort of represent where our game could be. Now, I'm not going to exhaustively cover them all. Again, I'm probably not going to make the most ideal solutions as we code all of this, but that's okay. I think it's better just to get something working and sort of go from there, and then we can refactor things later once we know more and realize why something does or doesn't work. So, that's roughly what the game state is. So it's just this thing that sort of represents it all. Well, one of the things that this is useful for is that we can create these functions that essentially take in a game state and return a new game state. Now, in this case, this quick example, we're taking in a game state, which is an object, and then we're, you know, it's this type, not an object really, but it's this type here, and we're returning a new game state. So, you know, we're not altering this one and then, you know, just giving them the altered one back. So that is an option. You know, a lot of times if you're looking at this, let me just go ahead and write some pseudocode. What you would probably do in this case is you'd say something like the return game state is going to be clone the existing game state, and then we'd operate on ret, and then eventually we return this return object. So we've cloned it, and then we've done some work. This is what we're going to be doing, partially because I think it's just easier for what we're doing right now, but also because I want to show you how a couple of these different functions would work when using clone, specifically the built-in copy function. I think it's cool to see how it works and to get a real example of why you might want to use it. So we're doing this. The other option would be if somebody passed in a pointer to a game state, you might then just, instead of working on ret, you might return nothing and just simply go through all of this and, you know, just change the game state inside of this function. So regardless of which one of those two you end up taking, I'm going to go ahead and undo all that. What the goal of this transformation function is, this deal function, for instance, would be to take something like this game state up top. So we've got a brand new game that's got a deck of cards, but players don't have any hands. So what it might do is it might deal all the cards and change the game state to hands dealt. It might update the deck because you can see here that it drew some cards from the top of this deck. And it dealt them in the order that you'd expect. So first it dealt to the player, they got the ace on the top. Then it dealt to the dealer, they got the 10. Then it dealt to the player again, they got the jack. And then it dealt to the computer again, and they got the 8. So from all of this, all 4 of those cards were taken out of the deck, given to the players, and then the deck was updated. So that's what you're seeing happening here, is this would be a function that essentially does that transformation to the game state and then gives us the new game state. And that's what we're going to be doing in this video, is taking all of this code we have in our main function and essentially adding a game state and then converting it all this logic into functions that just, you know, transform the game state into what we want it to be. So I think I covered this a little bit, but there's a lot of reasons for that. One of them is when you're looking at a game and you have a player jumping in a side scroller or something like that. Having game states and different stuff like that really makes it easier to sort of, or player states or different states like that can make it easier to, you know, error check, do a lot of different stuff like that. If it's something you're interested in, I definitely check out some videos on game development, something along those lines. That's not what I want to focus on exclusively by any means, so I'm just going to sort of leave it at that. So you probably also won't see this sort of idea, the game state idea, much in web development. And the reasoning for that is that in web development, you generally want to make a server that's stateless. You don't want to keep track of things about the user in between requests. Now, you do want to, in your database, you'll store some things about them, but it's not the same as a game state here, where you're expecting every single consecutive web request to be about the same exact user from the same user. And the reasoning for that is basically that whenever a person makes a web request, if you've scaled your servers across many different instances of your application, you want each one to be able to handle the request depending on where the user gets routed. You want it to be able to scale better, so you want it to be a stateless server. And instead, you expect the user to pass all the information they have about the request, and then you parse it all from the request, do whatever they need you to do, and then return the data to them. And then you're done with that. There's no state being saved beyond things you have to save in the database. We're going to start by defining our game state, and then we're going to try to provide a clone function. So you'll notice that when I talked about how we're going to do transformation functions here, I showed you that we're going to use this clone. And I basically want to just get all of the groundwork ahead of time, because every transformation function we have is going to clone the game state, and then it's going to return a new one. So we want to look at how that clone is going to work, especially with, as we'll see here, a game state that's going to have slices in it. So we need to look at how do we clone those slices and make sure that we're not accidentally altering the existing slices. So to do this, I think we first just need to start with the type game state, and it's going to have 4 pieces of information in it that we've talked about. So the first is the deck, and it's just a slice of cards. And that's coming from this deck here that we call deck.new. Will return a slice of cards. Okay, so coming back down here, the next thing is going to be the current turn of whoever's playing. I'm going to write integer for now. Long term, we're going to change that to be something else. It'll probably be a custom type just to make sure we're not getting random values stored in there. The next thing is going to be the player. This is going to be a hand. Again, this is coming from this stuff up here. We created this hand object, this hand type rather, that the hand type is used to represent, a player or dealer's hand, so that's what we want this to be. Lastly, we have the dealer hand. Okay, so before we move on, I think it's important to talk about this game state and specifically what cloning it is like. Trying to think of a good way to show this. So, okay, first, before we move on, let me say this is a slice. And this hand is not obviously a slice, but if we come up here to the top, you'll see that it really is a slice behind the scenes. And that's important to remember and to keep in mind, because it's also going to matter here. So I guess to test this, what we're going to do is we're going to just comment out. Actually, we'll keep the cards part. We'll comment out the rest of this. And what we're going to say is GS is going to be a game state. I'll say gs.deck equals cards. Actually, we can just put this. Comment the first line out then. And what we want to look at here is the fact that basically if we were to pretend like we were copying this game state, it's not going to copy everything we expected. So typically speaking, actually, let me go to the Go playground real quick. I think I can show this better here. All right, so let's say we have type demo, which is a struct, and it has something like a name, which is a string. And then down here, we have our D demo, d.name equals John. And then we'll say D2 colon equals D. So now if we call D2.name equals Bob, and now we're going to print out both of these. So we're going to say D equals D and print out D2 equals D2. So let's format this, run it. And you'll see here that when we run this, D2 ends up being a new demo object. So it's not the same one that D was. If we were to print it out right here, just before anything else happens, you'll see here that at this point in time, when we print it out first, it has the values coming from the original D variable. So this demo was copied, but it's not the exact same thing. We can change the name, and it will still ultimately, it won't end up changing the original D variable. It'll end up just changing D2. So this is important because we can use this just colon equals to basically create a shallow copy, I'll say, of what D was. So where this becomes problematic is if we have something like numbers, and it's a slice of integers, and we'll say d.numbers equals a slice of integers. We'll say 158. Then we'll do this d2 equals or colon equals d, and we'll print out d2 again. We'll put something here, original d2 equals, and we'll print it out. We're going to change the name just like we were, but we're also going to say d2.numbers equals int 4, 5, 6, and we're going to run this. And this is actually going to do what you would probably expect, but I'm going to show you where this can be confusing here in a bit. So you'll see here that original D2 is John 158 because it got this copy from D. But then here, when we print them out at the end, you'll see that the two are still completely separate. So they're kind of doing what you expect. When we overwrite numbers, it sets it for D2, but it doesn't change what was in D. So this is really what we want. But what I want to mention here is that while it seems like it's being copied over, the truth is if we were to do D2 numbers 0, d2.numbers 1 equals d2.numbers 1, comma, d2.numbers 0. So what I'm doing here is I'm swapping. Whatever's at the 0 index and the 1 index, I'm swapping those two values. And now that I've swapped those two, I'm going to run. I have this F at the end that I don't want. And I'm going to zoom this in actually a little bit so you can read it easier. So now that I've swapped those two numbers and I've run this, you'll see here that our code is not really doing what we wanted. It's not what we expected, at least, if we were expecting it to be a copy. So in this case, the numbers in D got changed for some reason. So what's going on here? The short answer to this is that behind every slice, there is an array that the slice points to. So it has a pointer pointing to some array. And while the slice itself got copied, the pointer is still pointing to the same underlying array. And this is something that's most commonly found in, whenever you're manipulating slices, or you'll sometimes see it with maps too. It will cause this sort of thing to happen when you don't expect it. And it's a little bit fuzzy because you're like, sometimes it seems like it's, passed by value, but sometimes it seems like it's passed by reference, like what's going on. And this is even worse, not worse, but it's more confusing by the fact that if I do d2.numbers equals append d2.numbers 1, 2, 3, and if I run the same code with that, you'll see that now it appears to be very different. What happened? Why is this not the same? So a lot of this basically comes down to the fact that, as I said, this points to an underlying integer array, and the slice is being copied, but the integer array is not being copied. In cases like append, the append function will actually sometimes cause the underlying array to be replaced with a new one. So a new slice is returned, assigned to d2.numbers, and that new slice has all the original numbers plus this new one. So there is some copying going on there, and that's why it's a little bit confusing. I actually have YR slices, I think something like this. Oh, I want it to be, assuming I got the URL right. All right. So I've got this article that talks a lot about why this happens, but for now, I just want you to understand that slices aren't just copied. Whenever you take this d2 colon equals d, that slice is not going to be copied. What we need to do to fix this is actually to make sure that we copy all of the things from d.numbers into d2. So the easiest way to typically do this is and you can do it this way, but I'm going to say that it's a little bit, you potentially have an issue. Instead, what I'd probably say is d2.numbers, or I'd do var d2 demo, or we just do d2 colon equals demo, and then we'll do name is going to be d.name, and then what we want to do now is we want to make sure that we have a numbers. It's going to be an integer slice, so we want to do make integer slice, and then we want to make sure we set the length. So whatever the length is going to be is whatever the length of d.numbers is. And now if we format and run this, you'll see that we've got a bunch of zeros here. That's what's in D2 now. But what we're going to do after all of this is we're going to say copy And copy is a built-in from Go. Let me look for it real quick. And basically the way it works is you pass in a destination and a source, and it will copy everything from source to the destination. The one thing that I do want to mention that can throw you off is that it will, this right here, copy returns the number of elements copied, which will be the minimum of the length of the source and length of the destination. So you need to make sure that when you're doing this, that the source, which is this, or the destination, which is this numbers in D2, has the same length of the destination, or the source, which is d.numbers. And that's why I'm using this make with a length already specified here. So with all of that, we can actually do d2.numbers, and we can do d.numbers here. So now we can format it, run it. It's supposed to be numbers, plural. And now you'll see that it's working as we expected. There aren't any weird scenarios that will throw you off. We can just make sure that we've copied all the numbers from D into d.numbers into d2.numbers, and moving on, we can do all of that. So what we want to do in our code over here is we want some way to take this game state, and we want to clone everything that we can easily, but then anything that's at a slice, we want to make sure that we copy it all over using that built-in copy function. And I will mention that this is not the most efficient thing in the world because we have to iterate over all the cards every single time we clone this deck object. So it seems really slow, but for a blackjack game, it's going to be fine. So, it's not a big deal, but that is why I mentioned at one point that, sometimes for a game, it might make more sense to just alter the game state instead of returning a brand new copy of it. But again, that's not the point of this video. I wanted you to see how some of this worked. Okay. So, I'm not sure why this is throwing an error. It's probably something up here. I don't know. I'm just going to comment that out. Come down here. Oh, I need to put struct here. That's why. So what we want to do now is add this clone function, which will take in a game state and return a game state, which is a clone of the given game state. So what I'm going to do here is say ret : equals game state. And one of the reasons you'll see me not do this is it's easy to accidentally forget about a new attribute or a new field on the game state when you do this. So for instance, if I was doing this and say the dealer hand wasn't part of the game state and later on I add it, so I do dealer hand, it's easy to forget to update this clone function and it'll look like everything's fine because we'll still be pointing to the original dealer hand. The downside to this is that we could potentially be altering the old game states and maybe for some reason that's important. In this case, it really isn't, but it could be. So by doing this second part where I just construct a completely new thing from scratch, anything that gets added to this game state type that I forget to put down here in the clone will just end up being the 0 value. So that's a little bit easier to detect and a little bit easier to be like, oh, something's wrong there. I need to go fix the clone function. So that's one of the reasons I'll do that. So what we want to do here is deck is going to be make, it's a deck.card slice, and its length is going to be gs.deck. And then we're going to, I'm just going to copy this 3 times because we're going to have player and we're going to have dealer. And both of these are of the type hand, and I don't actually need the brackets up front. And then for this last part, it's going to be gs.player and gs.dealer for the lengths. So those are the 3 things that we need to make the slices for. We're going to have to use the copy function on. And then finally the turn. For this one, we can actually just use gs.turn. That's completely fine. Okay, so at the end, we're going to return this object that we've created as our slice, or as our clone. And before that, what we just want to do is just do the copy for all 3. So we're going to say copy ret.deck, gs.deck. And we can copy this 3 times and just do player for those 2 and do dealer for these 2. And this should give us an ability to clone that game state and return a brand new one that has everything copied over correctly. One last thing I want to do before moving on is just add a helper function here to the game state. One that will return an address to the current player's hand. And I'm going to do it as an address because we have this clone function. I see our transformation functions looking something like this. So func deal, we clone the game state, and then we work on ret. The rest of we work on the cloned variable the rest of the way through. So knowing that, I think it makes sense to make this function that returns the current player's hand return an address so that we can manipulate that object that we get back and know that it's manipulating the actual game state that we have, so that's the one that's going to be returned. So this is going to be game state. It's going to take in the pointer to game state here because we want to get the actual address of the real thing, not like a copy of the game state. And it's going to return I need a function name. It's going to be current player, and it's going to return a pointer to the current player's hand. Okay, so now that we have all that, we need to switch over the game state's state. Yeah, the state's what we used. So when we're looking at these three states here, we basically need to figure out which of these do we want to return something on, and what do we do if it's an invalid state. So a lot of the times in code, you'll think, all right, if something's invalid or an invalid state or whatever, we need to return an error. In this particular case, I'm going to not return an error. Instead, I'm going to say default is going to be panic. It isn't currently a player. I don't know how to phrase this. All right, so we're going to panic here. So the reason for this is that if you ever call this current player function inside of your code when it's not currently a valid state, it's not like connecting to a database or something like that where, maybe the database just wasn't available and that's what happened. So we get an error back and we can retry later if we want to do something like that. What this infers is that there's a logic, issue with your code. For some reason or another, you're trying to get the current player when we're not in a state where there is a current player. And there isn't really a recovery from that error. It's more of your code is just wrong. So in this case, I think it's fine to put a panic here that basically just says, it's not a current player's turn. You shouldn't be calling this right now. So now that we have the error case handled, I think the next thing is to cover the two cases we care about, which are state player churn and state dealer churn. And for both of these, what we're going to do is we're going to return a pointer to the hand. So in this case, I'm just going to go ahead and grab both of these and do return gs dot. Apparently that didn't take with the copy. All right, and then I want a pointer to these. So we'll just do that. And that multi-select probably didn't save me any real time, but something I was just doing. Okay, so that's it for the hand function. We've got the clone function. I think we have everything here to sort of start writing these transformation functions. And in the process of writing those, we'll go ahead and we'll take a lot of this stuff here and we'll expand on it or change it if we need to. But for now, I want to go ahead and end this video and do it in a new video because I think this one's already gotten fairly lengthy. So now that we have the game state, before moving on to the next exercise, I think what makes the most sense is to come back through here and to take everything we have here in our main function and to take this all and to transform it into, or to basically create transformation functions and convert all this to use those transformation functions. And you're going to see as we do this that we can still have user input in some of these functions. That's fine. It's just important to sort of be able to represent all these different things that happen and smaller, easier to sort of test if we wanted, and easier to write and maintain functions. So I think we're going to start with, let's go up here to the top. We know we need an initial game state. I'm just going to go ahead and say that. So we've got this game state here. We're going to need some sort of function, if I could find this main here, that sets up our initial game state. So I'm going to call it func initial game state. It's going to return a game state. And this one is basically going to return, actually, I don't even think this makes sense right now. We don't need this. Okay. Looking at this, our game state is going to start with something like this. And then you'll see the very first thing we do here is shuffle the deck. So we take whatever deck we have, or we get a new deck out, whatever it is, and we shuffle it. So this sort of represents getting a new deck or 3 new decks and shuffling them all together. So what we want to add is a way to shuffle. And this is something that we might need to do, periodically within our game, not just at the start of the game, because when you think about it, a user is going to, how how do I put this? So basically, a user might play enough hands that the deck gets low enough that they decide, all right, we need to shuffle the deck, or get new decks, whatever it is. And casinos do this in real life. After so many hands, they'll take what they have left and they'll shuffle it, so you can't just count cards and know exactly what cards are left in the deck. So we're going to say func shuffle, which takes in a game state. We'll return a game state. And this is supposed to represent this whole shuffling section. So what we're going to do here is say ret is clone the game state. Ret.deck is going to be equal to this line down here. So this is us shuffling the deck. And then we'll return that deck. So we can replace this line with game state becomes shuffle the game state. And you'll see here that I don't have any real error checking. I don't have, are we on a valid, is the game state.state correct? I don't think it's super important for this part right now. Obviously, if you were building a really complex game, it might make more sense. But for now, I think this is fine. Where I really wanted those turns and stuff like that, or the states to be part of this state variable here, field here. What I really wanted that for is to sort of figure out which player's turn it is. Are we in a betting stage? Things where the user has a little more control, or the AI might have a little more control over what happens, and that way we can sort of limit what they can do. Okay, so the next part, when it comes to player and dealer, it looks like we just take the player and the dealer, and we, from the looks of things here, we just deal them a new hand. So that's really not that hard to code up. We could say func deal, takes in a game state, and it returns a game state. And you'll notice that in this one, we're going to clone the game state. But what's interesting is that the player and the dealer get brand new hands. So whatever was there, even though we've copied it with this clone, we don't really care about it anymore. Now I'm going to keep it because this also clones other things that are worth keeping in mind. But I think this is, something to keep in mind. So another thing that happens is after let's just deal with the hands first. So ret.player is going to become a new hand of size 0 and capacity 2. So I'm going to start with capacity 2, although realistically we can make this capacity maybe something like 5, because typically hands in blackjack aren't going to go over 5 cards. But at the same time, you very well could be more than 2. So I think this makes sense. And this is a situation where a capacity can be useful because you won't have to reallocate this slice here very as frequently, because that chances are I'm not going to use more than 5 cards. So the dealer is going to have the same thing. And then what we're going to do here is we're going to say var card, deck.card. And we're going to say for I is equal to 0, I is less than 2, I plus plus, because we want to deal 2 cards to each player. And again, we want this to go in the order of player then dealer. So we're going to say card ret.deck is equal to ret.deck 0, ret.deck 1 onwards. So this is our draw function that we have. I think, we still have it here, so you can actually use that if you want. Let me come up here and find where I am. So I could actually say draw ret.deck. But again, this draw function really loses a lot of its value, especially given that dealing and drawing isn't going to happen as often. It's going to be contained in these things, but I'm going to go ahead and use it because we have it. All right, so from there, ret.player is going to be append ret.player with the card. And then we're going to do the same thing down here, and we're going to deal a card to the dealer. And then this loop will iterate over twice, so it'll give each player 2 cards. And then we're going to say the state is going to become state player turn, because we know that after we deal the cards, it's now the first player's turn. So that is everything that happens in the deal function. And you'll see that this one's a little bit longer than shuffle, but it's pretty easy to see what's going on here, and it's pretty easy to understand the logic behind it, because it's all sort of a part of that, the deal step. So down here, we're going to replace this all. We're going to say game state equals deal, the game state, and that will replace all of this. So the next thing we want to do here, looking at this, you'll see is we want to let the player take their turn. So we need some way to sort of handle this. What do we do here? So I'm actually going to just leave a lot of this here. So what I'm going to say is if the input's not equal to actually, I'm going to say here, while the game state is currently state player turn. So as long as we're in the player turn, we're going to iterate over this loop. And in the loop, we're going to say the current player's hand is gs.player. And this is going to be gs.dealer.dealer string. So same exact thing here for the most part. We're going to read in the input, and then we're going to decide what to do. So the first thing is this case H. This is the hit case. So let's add a func hit. It's going to take in a game state, and it's going to return a game state. And again, we're going to start off by cloning, and then we're going to eventually return this ret variable. And you'll notice that I use the variable ret a lot for something that I plan on returning. You don't have to do that. It's just sort of a habit that I've gotten into. Okay, so now that I've got all of this, I think what makes sense is to think about what is a hit. Well, we have this all here, so we kind of already know what it is. We take the current player, we draw a card, and we add it to their deck. So what we need to do here is something along the lines of who is the current player. So hand is going to be ret.currentPlayer. And then we're going to say var card deck.card. And then we're going to say card, comma, ret.deck are equal to draw ret.deck. So we're going to draw that card. And then we're going to say that the hand is equal to append hand with the card. But I think, yeah, it's going to give you an error here because this hand from current player is a pointer. And, you know, when you call append, you can't give it that address. You actually have to give it a slice. So we're going to go ahead and give it, put the asterisk here in front of both of these. So we're saying that whatever value hand is pointing at, we want to replace that value with whatever the result is of appending a card to that value. Okay, so I think that's everything here, except there's one thing we could do here. Specifically, we know that if a player has a score over 21, if their minimum score is over 21, they busted. So we could add something here along the lines of if hand.score is greater than 21, at this point, maybe it makes sense to stand with the game state and return whatever that result is, and not game state, ret. So this is an option, but we don't have that stand function yet. We also know that down here, we're going to need that stand function. So we can say case stand. We want to stand with the game state, and the game state is going to be updated. And this one is the game state equals hit with the game state. So this is what we want this to look like. The default, we could print out something like invalid option. And we could print out input. That's fine. So we need that stand function. That's really what's keeping us from, moving on with the rest of this. So I think what makes sense to do here is just to write stand as another one of these functions. If I could get the capital letters correctly. All right, so what happens when a player stands? So we know that before what was happening was, if it was the player's turn, it became the dealer's turn. And if it was the dealer's turn and they stood, it went to the sort of scoring stage of the game. So from here, it looks like basically what ends up happening is we do something like ret is going to become clone of the game state, ret.turn, or it's state right now. So we increment the state. And this only works, at least right now it only works because I know that we only have 3 states. I know that I know the exact order of these 3 states here. If it's player's turn, it becomes dealer's turn. That's what incrementing it'll do here because I'm using iota. If it's the dealer's turn, it's going to become state handover. State handover, which means that the hand is over. If you change the states, this is something that a test can be very useful for. You want to make sure that this logic continues to work depending on if that code is changed. So this is something where while this stand function seems very simple, having a test could be very, very helpful to sort of make sure that the states don't get rearranged and it doesn't cause a big issue. So I'm just going to go ahead and leave it like this for now. I think it's fine. There's always a chance that this becomes problematic and we can fix it. At that point, I'd probably do something like switch on the state, and then we would decide, all right, if it's the player's turn, it becomes the dealer's turn. If it's the dealer's turn, whatever state we think makes sense to go into is fine. And if it's not player or dealer's turn, well, calling this is probably invalid at that point, so maybe we panic again or something. Okay, so that stand hit. Down here, you'll see we've got stand and hit. There's still a big chunk of logic here that realistically, this is the player's AI. So I'm going to leave it in here for the time being, but that's really what this is it's a player AI that's sort of doing, actually, I don't know if I want to pull it out or not. A lot of the next video is going to be taking this out, so I think I'm going to let it here. And you'll see in the next exercise, and you'll see when we do that we can pull this out and sort of customize it a little bit based on what's going on. So instead of being, somebody actually typing things in, we can have the computer decide what makes sense. The next thing we have here is the dealer's churn. This logic down here, this for loop that says, as long as the dealer scores in a certain range, we want to keep, hitting cards or hitting and getting new cards. So I'm actually going to replace this with something very, very similar to what we have up here. I'm going to say for the game state is equal to state dealer churn. And I think this becomes a little bit clear as to what's going on. As long as it is the dealer's churn, we want whatever's inside of this for loop to continue running. And basically what we're going to change this to is if the dealer's score is less than or equal to 16, or the dealer's score is equal to 16 or 17, and the min score is not equal to 17, meaning that they have a soft 17, we want to hit. So I got to replace all of these dealer dots, these first three, with gs.dealer, dot whatever they were calling before. And if this is the case, we say game state equals hit with the game state. Otherwise, game state is going to be stand with the game state. And as we saw before, that stand will go ahead and increment the churn, or the state, which means it'll no longer be the dealer's turn. So this code really isn't that much different, but I think it's just a little bit clear as to what is going on here. We very clearly know that this whole block is for the current dealer's churn. And again, this whole set here is essentially just the dealer's AI. So we could take this and pull it out and stick it somewhere else and have it turn into something that we could customize, or maybe we have a simpler AI for new players, and we have the standard AI for somebody who wants to really run a simulation as if they were playing against a casino. So here we'll get rid of all of this, and then the last thing I want to do is have something that sort of ends a hand. Typically what would happen with an end hand is you would have a function that would, if you had bets or something like that, it would go ahead and perform that logic. So it might take in the game state, it might clear out the hands because the hand is over, it might print out the scores, but then it might also update a current user's balance based on whether or not they won or lost the hand. So I think it still makes sense to put all of this inside of another function. And we're going to go ahead and just call that end hand, I think. So we'll do func end hand. It'll take in a game state and return a game state. And this might end up being way too big, and later we'll change it some, but I think that's fine. For instance, if we have things like wagers and stuff like that, it might end up becoming a couple different functions like payouts. Maybe paying out is one of the round or steps, and then another step would be clear out their existing hands. So like the dealer goes through and takes away people's hands. There's different stuff like that, but for now I think this is fine. And I'm going to do the same thing as normal here. We're going to clone the game state. Then I'm going to do ret.player.score and ret.dealer.score. Ret.player, ret.dealer. I think that's it for what needs to be changed, and then we're going to return ret at the very end. And I will mention that if you wanted to, since we're ending a hand, we can say ret.player equals, we can just say nil, and ret.dealer equals nil. So this is basically our way of, clearing a player's hand. And I'm actually going to add a print line here, just so that whenever it prints out busted, win or whatever it is, we get a new line that sort of clears out the, whatever was there. Okay, so that's all of that coming down here. This is going to be end hand, game state, and the game state equals end hand. Ooh. With the game state. Okay, so assuming that all worked, our code at this point should work. Should work exactly like it did at the start of, I guess 2 videos ago or something like that. Like when we had the game working. So we're going to go ahead and test this. All right, so 6 of club, 5 of hearts, that's an 11, so we probably want to hit here. All right, we got a 21, so we're definitely going to stand. And you'll see here with the final hands, the dealer busted. So they had a 6 of diamonds, 10 of hearts, which means they have to hit. They hit, they got a 10, and they busted. So it looks like the game's working. Let's go ahead and come back here. And you'll see that one of the things we could do, now that we have this all here, we know that shuffling is sort of, it's not something we do after every hand. We do it after maybe a set number of hands, or maybe we do it when the deck is below a certain level. So for now, I'm going to leave it outside of this, and I'm going to do something like for I is equal to 0, I is less than, are all these, yeah, there's no loops here. I is less than 10, I plus plus. Then I'm going to take all of this, put it inside of this for loop, and then we're going to go ahead and run this all over again. So here you'll see 9 of clubs, 7 of spades. We'll stand there. You'll see that we lost. Okay, so what's really important here is that it's dealt us a new hand, and you'll see here that the game continues to letting us keep playing hands. And again, maybe we want to hit here and we busted, so that's not good. Maybe we'll stand here just to see what happens. We'll keep standing, and you'll see that we've won a couple games so far. And we can keep playing through them, and we're getting new cards every time. And finally, after the 10th hand, the game ends. So this is important because it kind of illustrated how easy it is at this point to sort of make it so we can play multiple hands using the same deck, all of that stuff. All of this code we have still works with that all. It's not destructive in the sense that it gets rid of the decks. All of these things sort of interact as if they don't really care which hand it is, which is kind of cool about the way we coded it. All right, so that's it for this exercise. As I said, the next exercise is going to be expanding on this even more. After that, I'm going to be done with this. I don't want to spend too much time on the blackjack game, especially since it's already 3 exercises, and that's kind of the limit as to what I want any single topic to be. But beyond that, I do think the simulation stuff will be pretty cool, so definitely check it out if it's something that interests you.